This is part 5 of the series Limits, and at the end of the last part we looked at two special trigonometric limits, and we also looked at the squeeze theorem in order to prove one of those two limits. In the beginning of this part we're going to get some practice in using those limits and a little bit more practice in manipulation of trigonometric functions, which is going to be very necessary as we move through the course. Alright, so the first problem up here, we have the limit as x approaches 0 of tan x over x. Now this is related to one of the special trigonometric limits we learned in the last part, and that is that the limit as x approaches 0 of sine x over x equals 1. So our trick is to be able to manipulate this to see if we can use that new limit that we learned last time and use that to solve this problem. So is there a way, do you think, to convert this? Well, there should be, because tangent is simply sine over cosine. So let's rewrite this so that we have a product of a couple of different quotients. So what I mean by that is, let's take tangent and let's rewrite that as sine x over cosine x, and this 1 over x is just 1 over x out here. So this is the equivalent of this, and we have the limit as x approaches 0 of this. Well, given the fact that we have the two pieces we need, we have a sine x here and an x here, we can regroup these terms because these are just products and quotients here, so they're commutative. We can move those anywhere we want as long as we don't change the order in the numerator, and we should get what we're looking for. So let's do sine x over x times 1 over cos x. Now, one of the properties of limits that we learned we can apply here, and that is the limit of a product is the product of its limits. So we can split this apart into two limits. So let's go up here and split this apart. So this is equal to the limit as x approaches 0 of sine x over x times the limit as x approaches 0 of 1 over cos x. Now this is one of the two special limits we talked about. This is just 1, and we can do a direct substitution to evaluate this limit. Cosine of 0, as we approach 0 here, cosine of 0 is 1, so this limit is 1 as well, so this limit comes out to be 1. So the limit as x approaches 0 of tan x over x equals 1. Now let's go on to the second problem. Now here we have a similar situation, but we have a little bit of a problem in here. In this case we have sine of 4x over x. And let's think about this. Let's just call this 4x. Let's just make that some generic u function. And what we really want is sine u over u. That's supposed to be u. So we want the limit as sine of u divided by u as x approaches 0. That's what we want to change this into. So we got to think, what do we need to do to this to put it into this form? Well, that's all we really need is a 4 in the denominator here. So we can rewrite this simply by saying that the limit as x approaches 0 of sine 4x over 4x. Well, what we did was we put a 4 in the denominator here, and that got us this form. If 4x is u, then we have sine u over u. But the problem is we have a 4 in the denominator, and we have to offset that somehow. So what we need to do is we need to offset that by multiplying by 4. So this is 4 over 1 over here. So again, we have a limit of products, but we have this limit over here and this limit over here. So we can separate this out and say limit as x approaches 0 of sine 4x over 4x, this is supposed to be in parentheses, times the limit as x approaches 0 of 4, because that's all 4 over 1 is. Now this limit, just like it was up here, this limit is 1. And the limit as x approaches 0 of 4, well, we learned this is one of the other properties of limits we learned last part. That's just 4. It's always 4 because it's a constant. So 1 times 4 is 4. So this limit equals 4. So these aren't terribly difficult problems. You just have to look into the problem and break it apart and see if you can manipulate into a form that's convenient. This is going to be a process that's going to become very familiar to you as we move through the course. All right, let's move forward with the next topic, which is continuity. Continuity is a foundational concept. That is, it's central to many of the ideas we're going to be talking about as we move through the course. And by continuity, what we're talking about is, can I draw the graph of a function without lifting my pencil off the paper? That's one way to think of continuity. But there are 3 special conditions that are required to define whether or not a function is continuous. The first is, and we're talking about continuity at a specific point. So if we have some point C on our independent axis, then that meets this first criteria. Well, in this picture, this first criteria, this function fails because f of c is not defined. So here's point C, and it's not defined in the function. The second condition is that the limit as x approaches c of f of x must exist, which means that we have to have a function that we can evaluate to the same value from the left and from the right. Here you see in this case here, this limit does not exist. So this function would violate that second property. And the third property, as the limit as x approaches c of f of x has to equal f of c. And here we can see in this third case that even though f of c is defined just as it is here, down here f of c is defined down here, and here f of c is defined here, the function is still discontinuous because the limit as x approaches c of f of x is up here, not down here where it's defined. F of c is here, this is the limit value up here. So this would be f of c here, and this would be the limit value. So we can see that this violates this third property. So these are the 3 key properties to defining continuity at a point. Now we're going to extend that idea to continuity on an open interval. And that simply says a function is continuous on an open interval if it's continuous at every point in that interval. Now we can see in each one of these 3 functions, with every other point from A to B, notice that A and B are an open interval because it's not defined at A, not defined at B. For every point in this region and this region, this function is continuous. Same thing here. From here to here it's continuous, and from here to here it's continuous. From here to here it's continuous, and here to here it's continuous. However, this function is not continuous on the open interval A to B. It is continuous on the open interval A to C and C to B, just as this is continuous on the open interval A to C and C to B. Well, actually A to C is not an open interval, it's a semi-open interval. But this function is also continuous on A to C and C to B, but it is not continuous on A to B. So hopefully you can see that very subtle distinction. So these functions, none of these functions are continuous on the open interval A to B because they're discontinuous each at a point, but they are continuous on subintervals inside that open interval. Let's go ahead and look at a couple of examples and see if we can solidify some of these concepts. In this first example, we have the parent rational function, and we can see clearly that this function is not defined at x equals 0. So that violates the first property, that at the point x equals 0, this function is not defined. So this function is discontinuous at x equals 0. But we can go beyond that, and we can look at the domain of this function. We know that the domain is negative infinity to 0 and 0 to infinity, obviously non-inclusive. And in this interval, in this subinterval, we know that the function is defined at every point in this interval. So that passes the first criteria. Same thing here. In this subinterval, the function is defined at every point greater than 0 and less than infinity, greater than negative infinity and less than 0. We know that because it's defined, if we look at the graph of the function, it looks something like this, and we can evaluate the limit at all points in this subinterval and this subinterval as well. So we know that the limits exist in these two subintervals, and we know that the limit of f of x at any c value in this interval is going to be f of c. And the same thing here. So all three criteria pass for this subinterval and this subinterval. So it's not continuous everywhere, but it is continuous on its subintervals. But we would say that f of x is discontinuous because it is discontinuous at a point here. All right, let's take a look at the next one down here, and we can say this is the difference of two squares. So we break this apart. X plus 1, x minus 1 over x minus 1. These cancel out, and we can see that this function has a discontinuity at x equals 1. So if we look at the graph of this function, it would look something like this. X plus 1 goes something like that, and there's a discontinuity right here. So we would say this function is discontinuous at x equals 1. And so this function is not continuous at that point, but it is continuous everywhere else for the same reasons that we are up here. Let's take a look at this one. This is a piecewise function. And if we look at the graph of that, let's do it up here. This would look something like this. It's defined down here to 0, and then we have something like this up here. So this function is defined at every x in its domain, and the domain of this function is negative infinity to infinity. So it's defined at every point, so that's the first criteria. We can take the limit of this function at every point in that domain, and the limit does exist, and the limit at any point in this interval is f of that c value. So this does meet the criteria for continuity. So we'd say this function is everywhere continuous. Now for our last problem, the graph of sine, very, very roughly, looks something like that. And since sine is a cyclic function, and the domain of this function is negative infinity to infinity, and we've already learned that the limit at any c value on its domain is f of c, we've already learned that, you can do it by direct substitution, that this function meets all the criteria for continuity. So we would say this function is also everywhere continuous. In the next part, we're going to extend our ideas of continuity And so I will talk to you in the next part.